All right. Okay. So welcome everyone for our lecture 4 in cloud computing and big data. Today we have a very basic topic, virtualization and data center design. And this is a little bit out of sync. As I said to you also, we rearranged some of these lectures more for students to start early in the assignment. Usually you would take virtualization as one of the first lectures really in cloud computing, because cloud computing is all about virtualization. However, there's also another course from Ingolfur that's teaching that a bit more in detail. So we basically over the years also agreed that the virtualization that I teach here is very, very, short. I instead, of course, focus more on the data center design. Here's also the good fortune that we got the invitation from Borealis data center to look in. That will be quite interesting. I cannot confirm exactly which date right now, but the boss of Borealis already said no problem at all. We just have to basically agree on a date and time. I hope to manage that within the teaching times, right? Of course, but we have no confirmation on that yet, but I keep you posted. But before we go into the material lecture 4, which is all about data centers, how they operate, how they achieve economics of scale, which is a very important term, let us review what we had the last time. And the last time was really extremely practical, although we connected to lots of theoretical fundamentals we had in lectures before, starting from lecture 1, lecture 2, etc., with machine learning, let's say principles, but then also very practically in the idea of building pipelines. We used a very, let's say, simple classification algorithm, if you remember, that was basically logistic regression to achieve binary classification, which you see a little bit here, but we also have always reviewed a little bit in context as crisp DM steps, right? So rarely you throw machine learning at a problem. You first have data exploration, you have data preparation, and then along the road, you start somewhere with machine learning, right? Especially in practice. And what we learned, for instance, by doing this with data exploration, we have seen a binary classification cannot really be done because there were not really two classes. So we had to subsample in the data set to make the binary classification problem really existing, and to have also this labels properly, which was then a pass and fail and not with conditions, or which was more funny, perhaps restaurant not found, right? There is no information. And of course, that means also stupid data sets, because they are properly with the restaurant can't be found. Also no violations that have been noted. But this is a typical problem in almost all machine learning, basically problems I'm facing in practice with my research group. You always have to understand the data first, see what is noise, what are problems in the data before you really then start with somewhere machine learning. Then we also learned more and more the concept that we basically have a training set and test set. If you remember, basically in the idea of our pipeline that we then have built, we have first fitted a model using the training set that we had. And then basically after that, you basically use a test set that you throw in the corner and use it for evaluation, which was then after training, we reuse a logistic regression model just basically for doing another test, and basically have then hopefully similar results. Now, the also message you got basically is the idea of the pipeline. So we have seen the same, of course, I do in the training, I also have to do in the testing. We had the idea of basically then have all this text of the violations tokenized, so putting it into words, and do a hashing function in order to prepare the data for the mathematical model. And the same ways, of course, you have to do it for new data coming in the test set, or later if you basically deploy this logistic regression model really in practice, maybe for these guys checking these restaurants, then you basically need the same steps again. Of course, they have text with violations, throw that in. So this is the beauty of pipelines that you basically have seen there. And with this, we also build up and up the very practical point of thinking how machine learning works, right? We start with the idea that somewhere there were training examples, which is very important. In our setup, this was supervised learning. So we have this guiding labels Y always given for all the feature X vectors, which was, of course, our violations. And what we had in our case was pass and fail. That was a label. Now, we also learned that there's several things we assume, like a probability distribution, which is a specific form of learning. We call that probabilistic approximately correct learning, PAC learning. We have to assume this so that the training examples will basically not be coming from some completely different source. And the unknown target distribution was essentially something which would be the ideal function that we never know. Something has in the past generated this data. The beauty is both top things you don't need, but we have to assume then otherwise machine learning wouldn't work. Then we basically go further and over the last couple of lectures established the idea that machine learning really has two main ingredients when it comes to practice. Again, you would have said there is a hypothesis set that I have in my toolbox. I can use support vector machines, I can use artificial neural networks, or I take the linear regression model. They all come with a sort of learning algorithm or optimization technique inherent in the learning. For instance, for the neural networks, we have so-called backpropagation. We'll come to you in lecture 8. For support vector machines, you have quadratic programming. And for our basically binary optimization problem, we pick logistic regression. We didn't have to. We could also set here, instead of using logistic regression out of our hypothesis set, we use support vector machines. They also do binary classification, right? So it's something what you have to pick, what you have to decide as a machine learner, is that a proper model for the given problem at hand. And then through iterative learning, which is basically in all of the machine learning problems in one way or another, an optimization problem, you basically have seen that we use, for instance, SGD as an example here to have some error function that we basically try to minimize. And then by this optimization over iterative learning, come then to this, let's say, final hypothesis, which hopefully approximates F well as much as we can. Right? Again, the notion was machine learning 100% is impossible. If usually this is the case that you have 100%, then there's a trouble in your model. Or it's a very toy problem, right? So usually there's noise, there's something that you cannot really achieve to make 100%. That's just something what we call overfitting, usually alarm bells in machine learning when 100% is existing. Chances are you didn't use regularization or validation methods. But this is done really advanced machine learning course material, which really needs to be taught in every machine learning course, not necessarily here much, but we will iterate this again also when we have neural networks with weight decay and so on. And of course, we use Spark underneath. There was the idea really what you also do in your assignment, thinking about having more course available. And here you have seen this equally means a lot of cost. If you remember, we had now something like 4 euros per hour. But when I steered it up to 30 or 60 workers, it quickly came to 80 euros per hour. And this were just not the perfect course available, right? We could then have the gigabytes of memories, which are really, really good. And then suddenly you pay maybe hundreds euro per hour. Also, the message is, although you don't use it maybe, right, the cluster itself is running on the cloud and costs. Right, so it's pay-per-use already, although nobody maybe from you do the assignment and my research group is not using it. We pay for it, that it's basically there 24/7 and running already the Spark instances. So basically, we already pay all the time, although nobody's using it. For a startup, this means also had a lot of thinking. So when I should put the cluster up, when I should put the cluster down, because otherwise you run into costs that you basically don't really need. Something to consider. What many people, I think, and many startups have lost a lot of money already. But let us come to the material of today, virtualization and data center design, more a conceptual topic, because you now have some practicals to deal with in MS Azure and then also using some Spark, Jupyter Notebook. Here now, this is something what we should have taught basically at the very beginning of the course, because cloud computing would be basically impossible without virtualization techniques. Here we keep it to a moderate degree. Again, virtualization really is a, let's say, short introduction. What are virtual appliances? What means virtualization? And of course, I pick here different pieces like migration topics, which are for data centers crucial, right? So this is something what we will talk about today. Virtualization in one respect can be probably taught across 5-6 lectures. There's lots of material, especially if you go into the details of the operating system and so on. But in the end here, it's just more for us to understand than data centers. And of course, the data center is best explained when you go basically practically touching metal, as I said. So luckily, we go to the Borealis Center that you see really racks in action. Here we basically talk then about several different pieces, how basically this data centers are really created. One key term you need to really learn after this course, ours today, is really economics of scale. why we have this Google data centers, which are several football and soccer fields large. There's a reasoning behind it, although it's basically a whole risk to have a very big physical center at one location, but it enables economies of scale, and we will talk about it. Then, of course, how you construct a data center. It's not that you can now just, with this nice floor here, for instance, thinking about putting some racks here, and then think about also the heating in the room, the cooling in the room. There's lots of infrastructure which is surrounding in a basically data center design, which actually alludes to lots of money that goes into it. We will talk about it, that 1/3 perhaps, for instance, is just cooling for a data center, right? Hence the idea of bringing lots of these data centers to Iceland, because we have ambient air cooling, we have quite nice areas where it's already cool, so we don't have to chill down so much. And then we talk about a little bit the first idea of public, private, hybrid cloud. So how you would now then basically do metrics on this, how you basically would deploy these clouds. This has something to do with, basically sharing models with the public or keeping some private data, perhaps as your premises, and then combining that smartly in real life cloud installations. So from the virtualization perspective, we come back to one of the first slides I've shown you. Essentially, when you take away the message what we had in computational grids just 10 years ago, the real big jump towards to commercial clouds and internet clouds was really through virtualization. So HPC machines that fueled the computational grids at that time had used very rarely virtualization. So you had more physical machines and really users using these physical machines, while virtualization enabled something called logical machines. Basically, many people could share logical machines on one physical device. And that was really the breakthrough that bring internet clouds essentially forward. Of course, alongside this was that computation and data grids at that time didn't have this swipe of credit card idea. Essentially, this was also introduced with the cloud computing, make it very simple for users, swipe your credit card, get charged, and then you get access to computing. And this was basically now the key ingredient. So let's talk a little bit about virtualization concepts are. Is someone of you already in the cloud, in the course from Ingolfur about virtualization? No one, okay. Well, this might be an interesting course. I thought it's one of the basics course, basically, but maybe it comes down the road. But it's not a problem because we will face anyway all the different basics here in this virtualization art. But when you think about the idea, what we want to achieve with this and the key ideas to leverage this was really resource sharing by many users. When you have one big physical machine, one big physical cloud data center, you have, of course, many different users at the same time you want to cater. And with this, basically, it makes it much more easier to do this with a virtualization layer and have then different applications at the same time running. You see a little bit here the difference, which basically highlights this, that you have some form of a hardware, very physical, of course, memory, CPUs, etc., etc. You have a hardware, a host operating system, and then your application. That is essentially what you have on your laptop usually. Some people have probably dual boot, have Linux and Windows or something like this. But in the end, this is a traditional way how you would have done it. Now, virtualization enables us now with a hypervisor or a virtualization manager to introduce a layer that basically abstracts now basically from the hardware and creates so-called logical hardware, virtualized hardware that in a sense don't really exist. But of course, it exists in the physical world one level lower. Right, so you would have a host operating system that is essentially taking care of the really physical devices, but you expose those logically and virtually via this virtualization layer and share it. So many people can now use that at the same time. And you see also with a guest operating system, so basically you can have here maybe Linux derivatives and then here basically Windows somewhere. It doesn't really matter, could be also CentOS, something else. The point is through this virtualization layer, you kind of encapsulate with virtual machines, basically how you use the hardware. And this is, of course, now nice flexibility. Think about that the users don't have to agree on a guest operating system. They can have their own ones. They have pre-installed applications. And this is, of course, something which is now basically the idea on scale we're going to use in the data center concepts. But, of course, was first developed also for normal computers, for laptops, and so on. So a very important ingredient, essentially, in the development of going towards data centers. And today you will find lots of different vendors. I will show you a little bit about VMware and Zen and so on. But Essentially, there are several different vendors that are in the field of providing this. And always the key idea is really thinking about the physical machines and the hardware that needs, of course, to exist, right? Also, a cloud data center, we have seen, we swipe in the credit card. In the end, there must be somewhere a data center having really hardware. It's coming in, not out of nothing. And the idea then basically using several ideas of different deployments, how you can achieve this with virtual machine managers. You see here basically that your comparison again through the typical machine, how you would use it, let's say alone, by just using the operating system, managing all the hardware, and then have your application on top. While here, basically, we have the virtual machine manager taking care of the hardware and exposing it to a guest operating and then guest application. So a similar picture we have seen there. Here, just think about the rights, right? That is now the key idea. While basically, you would have the point that the operating system has a full power of your system, of your laptop. Usually in this, let's say, deployment, it's called privileged mode. It can basically do a lot with this hardware. The VM hypervisor takes that away from your own operating system that you do as a guest. In other words, if you are having and living in a VM space, your rights will shrink what you actually can do on the system because you're sort of in a sandbox in this virtualized machine. And this is, let's say, one idea where, of course, there comes some security aspects into the game, which makes it also easier for data center operators to not give you full control over the hardware anymore, right, with interrupts and so on. So this is another interesting kind of key ingredient, how you do and create data centers, very important basically in the development. And the idea of making these abstractions and using them is basically something which I already was just explaining, the security, and using the same concept now at scale, which brings us to the data center, is of course something to think about. And this virtualization is of course a scalable approach as well to a certain degree on one device. So you can see here you can run different ones, different guest OSs as we discussed on top of the VMM basically, but of course it's also limited by the hardware capabilities physically, right? When you now start and say I have 1,000 VMs running on a very small laptop, there will be so much resource sharing and so much, switching between different users. It will be also not practically. So there are, of course, physical limits to this virtualization scheme. But when you do this, there's some, let's say, interesting approaches that we can employ them that I will talk to in the basically data center design that we will talk later. And another idea that is, of course, there is now the resource utilization. When you think about this is your own machine, it's just you using it or you're not using it. So the system is idle, maybe here and there, it's just running. Your laptop is there, no one using it, failed investment for a company, right? Now, when you think about the right-hand side, you would say one user is not using it, but perhaps 10 other users are using it. So it's not so much idle than having a dedicated, let's say, machine for everyone, right? So here you talk about resource sharing and can use the cycles where needed. And this is often also that basically the kind of server utilization goes really incredibly up, right? You see here when you think typical servers, you would deploy, for instance, a Spark on this kind of device, everybody would kind of have their own Spark. Then you basically would be probably by 5 to 15% utilization, while basically you have a shared cluster somewhere, maybe even in the cloud. When you share this with this virtualization idea, then you have 60 to 80%, just because your hardware is all the time used by different users. And that's what you want to achieve, because think about it, that this is all still sort of, not really existing. It's so-called fake. What's really costs is hardware. That's where the company is basically investing in, right? And when this hardware is not used and lying around and is idle and not used, then it's of course bad for the company. They invested lots of money. Assume now a Spark cluster we have created and we have built this. We built 60 workers full of gigabytes in memory. Nobody's using it, but we have paid a lot of money for it. So this is very bad for a company. We want to increase the server utilization. And this was starting already in on-premise resources. So basically on data centers within companies, virtualization was introduced, a very nice development. And then of course, there were different techniques which then virtualization can leverage, which today are basically totally normal operations in a data center, which also fueled a little bit then the aspect of really making it at scale and the commercialization, because you could do very nice things. One of it I already explained, of course. When you think about, you have hardware investments, you talk about multiplexing. So you basically can use on one virtual machine manager many, many different VMs, right? So this is a nice scaling approach. We discussed about it. That's okay. But the interesting thing is also what basically this virtualization enabled was dump things to disk. Suddenly your whole status, your running of the operating system, your application that you're running could be just dumped to disk. And then basically that saves space and also for running then on this virtual machine manager, many other VMs. So I think some of you have probably played with VMs already. You can basically store them and then reactivate, resume them. And this is, of course, a very beautiful idea, thinking about the data center when they have many, many users and some users are really idle, don't using the machines, then we can easily dump essentially this installation of the VM just on the storage. Suspension is it called? Of course, that means some time it takes, right, to dump it to storage and to resume it, which is here the provisioning then, because once it is on storage, it needs to be reactivated, become access to memory, become again to the hardware infrastructure where it's really executed. However, this enabled also very nice approaches for data centers, but the most, I think, crucial one in the operation, because when you pay, you assume a certain kind of service level, quality of service, right? When we don't say we swipe the credit card in MS Azure and hardware is failing all the time, then we don't want to pay for it, right? Hence, this live migration is here another part where you say data centers really benefit from it. Why? You can imagine if you have a Google data center, which is 8 or 10 soccer fields large, just racks inside and computers, hardware fails every minute. Right, it's actually already true in my center where I come from in Germany. Our hardware constantly fails, right? We are about to have an exascale machine and the whole room is full of computers. There's always hardware failing constantly. So you need in the software basically an approach that here and there basically can just swap essentially the whole application to something which is still running. And the hardware errors we will discuss are very many different ones. Could be the CPUs overheated, cores overheated, the memory failing. There's no access anymore to the parallel file system. There are lots of errors, and that happens all the time, constantly, right? Hence, the software must be ready for it. And this is virtualization layer. All what you do, you shift away essentially the application that you see here to something which is still running properly. And of course, there's self-diagnosis all the time in this virtualization layer to really recognize, hey, there's a physical hardware failure. We have to live migrate. An example I brought to you just that you see how in which time frame we talk about. So on the left side, that's not so important to understand. It's just basically coming up to a downtime after you're running a VM. But this is quite interesting to realize that essentially by doing this pre-migration, already knowing there is somehow a failure, probably not confirmed, but we have basically indicated that some chip is getting too hot, so it may be fail soon. You basically see that the swap time, the real downtime then of your service of what you basically have put into the cloud is in the areas of milliseconds. So you don't really feel it, right? So you still maybe have to reload because you're lucky just having here a request done to your Spark engine and doesn't respond. But with this, you have seen the live migration, which is now, of course, helping users to just continue even if failures always come to play. We will talk about this more and more also in lecture 5 when we have MapReduce, because the software has to follow suit, right? There's something which called resilience, that really this software is resubmitting job or whatever else it is in order to live with errors all of the time. And this is a bit different, for instance, today in high performance computing, when we have this large center for HPC, there's a weather simulation, it runs through all the cores or uses, I don't know, 2000 GPUs at once. One GPU fails, I have to resubmit the whole job again. And it was maybe running for 48 hours already. So this is lots of computing time burned. And this is virtualization layer and the data centers. This is something what they can prevent with this. Of course, then here and there, some operations are definitively not as fast as you would say on a HPC machine, especially when you think about parallel file system, parallel access to disk, very fast. In the cloud, this is all much slower. But it gives you the resiliency, which is also important. Let's talk a bit more about this typical, wording terminologies, virtual appliance, that you know a little bit about what that means. For instance, in MS Azure, there's also a part where you can create your virtual appliances and your virtual machines. Usually you have to pick here an operating system that is already pre-deployed, where you want to basically have then your application on it. But you see basically all clouds in Amazon, also in Google, you can always basically create yourself virtual machines there. Very famous ones that we will look at, that AMIs, Amazon Machine, which is basically having already deep learning packages deployed. Very nice material, because that takes a lot of time usually to have all the deep learning packages, installed together, running together in a concrete versions. We will look in this also when we come to lecture 8 and lecture 9 and so forth. So this is quite nice. Again, this is of course the cost effectiveness of large systems that you can achieve with it. And you don't have to use, of course, now Spark or MapReduce engines that we had. Maybe just this is enough already for you with the VM server that you see here. Just that you see you basically can do this. Also in the clouds today. You see here also that there are these catalogs, which basically have already installed and configured really good settings, not only for this essentially different operating systems, but also here and there you can really select several elements to it. For instance, containers we will talk about. Some container solutions are already pre-existing in this. Or as I said, the AMI of Amazon is another very good example of all the deep learning packages. So often, of course, it is very plain, just the operating system, because then on top you can actually do this. Also take away the message, as soon as you basically have this VM operating, if this virtual appliance is active, then it charges, right? It's the same way. So basically it needs a physical resource. Obviously you need a real hardware underneath, and this is something what you also have already to pay in the VM world. Even though maybe you don't use it for anything, but you already deployed it, you already basically have an instance running. Of course, that's not the case if you put it down. You have the opportunity as the Spark cluster to just drop it again to disk, as we have seen with the suspension. Then the costs are basically just on the storage level. But if you have it up and running, the appliance, if you use it or not, again, it will cost you. One thing I didn't mention is also, of course, the idea of copying VMs. I think that's also quite nice in some research groups or some businesses. You just copy VMs and then, can modify this. One has prepared a very nice engine, perhaps with Spark, and one is using it for this particular application sets. And another one is doing completely different application sets, but can share the same basic VM where the Spark clusters and everything are already pre-deployed. So a very powerful tool that you can create. And in that sense, you can create with templates often all these configurations, and from these templates you can create then, let's say, the very specialized VM that your company needs, which is of course very nice, because then the administrator has just to do it once, configure it properly, and all the users can derive a VM instance from that configuration, which is again a nice area of scaling. Of course, we do this in a data center on a much higher scale, which we will see probably also mostly in the second part, of course, when we talk about data center design. But you see also that there are many players. KVM is very known, Zen is known, VMware. You have heard from VMware, maybe? It's one of the most users that have actually do this and have a very, let's say, huge set of services and huge set of ways how you do virtualization. We will learn this a little bit in a video. Of course, I'm not paid from VMware, as you know, but it's quite a powerful company in this area. Also open source, there are some hypervisors available. Just to give you a real life idea, what I showed you before was also just more conceptualize it. Here you see now how Zen works, and you see also it's the same concept as having hardware devices, so real memory, real CPUs that you abstract away with the hypervisor, and in a basically domain which you then can choose in terms of an operating system. You maybe have Linux, you maybe have Windows, it doesn't really matter. And in these domains, you run then different applications on top. Different users can access it, and it's quite nice. Domain 0 is a bit special, which is a speciality now of Zen, of doing this to always access the hardware and so on. But this is usually also something where you typically have not the normal users accessing those, but rather for tests and so forth. So you see really different are there out there. So if you want, you can also work with some of them, KVM, Zen, download them. VMware works basically in different services the same way, I should say. Of course, as I said earlier, there are lots of different ways how VMware is now pushing virtualization with workstations, but also with big, large, clusters. Also, we will also see that a little bit in the video. Of course, it's a market for them, clusters and smaller server installations. So we're not talking about here always about your laptop, making that virtualized, but also really server farms and so on. So also here, you don't need to know that all by heart. VMware is also progressing. If you Google around it, you will see many products. Of course, still the idea of abstracting away from the real system hardware, CPUs, memory, as I said, storage, via basically this virtual machine manager is very important. Here you need you basically need some access. That's why you have usually supervisor modes here, so you can really change. While basically on the higher levels here, where users are going, they have, let's say, requests basically to the hardware, of course, but it's basically abstracted, and you cannot do very much changes if you are in the guest operating system. As we discussed, the same principle in VMware as everywhere else. And yeah, basically it continues with the idea how you essentially use it. Here you see, of course, an interesting element that you can combine those things, right? When you think about, you have now the CPU and all the hardware. Of course, nothing prevents me to say there's a host operating system I have on it, and I use it with my applications. I think some of you know that a little bit from dual boot. I don't know if you use it. Who has Linux and Windows on your system, right? So some know that concept. So you can have, and maybe let's say it's an application example, your host operating system would be Linux. Then you can have Linux applications on it. You can work with it. You can maybe code. And then your manager says, we need Windows PowerPoints. It's a common case in companies, right? There is no here basically open PDFs or so for slides. We always share all PowerPoint slides. So what you do is you have a virtualization layer. So basically create VMware, a solution. And basically your guest operating system is Windows. And then you can funnily exchange PowerPoint slides with your bosses that always need this. And basically you yourself have still your coding on one hand, and then basically the presentations nicely with PowerPoint and Windows on the other hand. The same goes actually for Excel, for other banking and so on. There's a very common procedure of using now this kind of mixed way, which you of course find also in practice a lot. And we have seen also some here in the course even using that. KVM is another player, and keep repeating myself so I get a bit faster. So just you see that, of course, they all embody this concept of this virtualization layer. That was a bit too quick. And some have a, let's say, other approach of a guest operating system. You see here a Para-Virtualized, which more or less does very similar things we have seen in VMware, just that some of these kind of calls replace really OS instructions in a different way. We have seen from VMware. That makes it para-virtualized because still some calls are then really going to the really physical layer in memory and CPU, for instance. But this is also something where it comes into the internals of essentially how you use KVM and so on. So it's something that you don't really need to know here in the course. We rather, again, want to focus on the data centers. So coming to data centers and basically reviewing another slide we had at the beginning, where I should have then continued with virtualizations that we did some applications, machine learning, and then also learn Spark. You see really that fuels the concept. So all the internet cloud is full of these hardware and storage and really physical devices. You can always think about it. This is now really virtualized resources usually, so that the software running on it can be nicely shared with many different users. The network is basically set up in a way that's really protected against, let's say, single individual users that not really have the access rights to really change there very much. And this is now fueling cloud computing a lot. Hence, we have to scale up a bit from the simple laptop that you have seen often, or that I basically had in a small scale. We now think about the bigger picture, like how basically virtualized resources here in the data center play a role. Needless to say, the basic physical resources are still there. Even in a very big data center, Google data center, where you go, physical hardware is there, but very quickly you see there would be a virtualized platform of sort existing where all the virtual machines basically are running on. However, of course, if you're a large data center, you need some management layer, right? That really looks, okay, which of these virtual machines are failing? How many are actually used by the users? You need some form of what you see here in integrated management that does a load management. Is one physical, basically resource overloaded, is not operating again, let's activate more others, data security management, etc., etc. And then on the infrastructure services, of course, you want to have billing as a cloud computing. So that means probably you want to have some good monitoring, user management, basically saying how many resources are used by whom, so that you basically, although you have swiped already your credit card, you want to have a good billing statement. We will show you that basically in MS Azure, also in one of the practical lecture, how we now eat up resources in the cloud while we actually sit here all together. Happily, the billing is happening and MS Azure makes nice money. Right, so this needs to be all in place in the data center because, of course, proper bills have to be put out. It's basically all a proper business, so it cannot just say, well, you use probably around 20 cores or something wishy-washy, which we would call it in Germany. Yet you can't do. You have to have proper statistics, accounting, billing, who was using what at what time for how long, etc. But by doing so, the nice thing is that we will see is we have firstly the idea of resource sharing. Basically, you have a cluster here with an internet. There's lots of different servers around it, and now you can really do this with resource sharing because it's basically physical hardware virtualized. And then basically also think about disaster recovery. If something fails, we have seen essentially with this live migration in, for instance, a big Spark cluster, we have 60 workers, one worker fails, overheated. Basically, MS Azure can quickly get another worker without us even noticing, right? With this today, very quickly done. And this helps us for maybe lots of different problems we have in terms of living with the faults. We will talk again, because hardware is always failing, as I said, constantly. Now, doing this on a data center, that's one of the last slides I want to show in the first part here, is really just thinking towards a different scale. Now we have basically this interesting physical cluster that you essentially see here. So in the end, it looks very homogeneous, very nice, but it's basically put into logical parts with all this different color encoding. So this again says we different users use all with the same principle of virtualization, essentially this kind of idea of a physical cluster, but it's virtualized, so different sizes for different users that have different payments, that want to maybe have Hadoop here, Spark there, or just plain vMsphere. So you have a very nice flexibility while the physical hardware is really utilized to the maximum degree. And the ingredients for this stay the same: multi-core I/O devices, many core. All of these ingredients, of course, are the same we discussed at the beginning of the lectures. Right, and then the example I give you in the video is a little bit now in server installation of the VMware. So let's look that a little bit up. And of course, there are also suites where you do this a little bit on the user space and have lots of exciting applications. And we will talk about this also later when we contrast it a bit to open stack and so on. But I think the video really captures the main essence that we should basically look a little bit in right now. It's a bit a longer video, but I think it captures nicely the essence of this data center virtualization.
The demand for IT services continues to rise while IT budgets remain flat. This makes it increasingly difficult to manage growth, especially with a complex, siloed IT infrastructure. Siloed data center structures create governance problems as vertical, per-application infrastructures make centralized management and future growth nearly impossible. Fragmented maintenance and management increases total cost of ownership because applications cannot scale easily when built on silos of isolated resources. Data center standardization and consolidation through virtualization is the key to breaking down silos and reducing capital expenditure, eliminating inefficiencies, and meeting increasing growth demands. At every level of the data center, from compute to storage to networking, there is a need for rapidly provisioned, on-demand capacity that is reliable, highly available, and highly scalable, so that IT can deliver virtualization economics across the entire data center. Server virtualization allows physical servers to be partitioned into multiple virtual servers. Each virtual server runs its own operating system and applications. Server virtualization facilitates management, improves scalability, and reduces capital expense by reducing the number of physical servers in the data center. Virtual server growth has led to an increase in storage and network demands. To keep up, the proven principles of abstraction, pooling, and automation can be applied to standardize the storage and network layers. With software-defined storage, physical storage is decoupled from the virtual workloads. Storage resources are then abstracted to enable pooling, replication, and on-demand distribution for higher availability. The result is a storage layer much like that of a virtualized compute. It's standardized, aggregated, flexible, efficient, and scalable. With software-defined networking, the logical network is decoupled from the physical network topology. This allows IT to treat their physical network as a pool of transport capacity that can be consumed and repurposed on demand. The result is multiple logical networks that can be dynamically provisioned and managed, all utilizing the underlying physical network as a simple backplane. As we move into the mobile cloud era, the same tools and processes used to virtualize and consolidate your on-premise data center can be used to facilitate your move to the hybrid cloud. In a hybrid cloud architecture, services from multiple heterogeneous providers can seamlessly be managed as if they were all part of a single virtual cloud. You can seamlessly move workloads between your data center and your hybrid cloud without having to re-architect your environment. More than 250,000 customers worldwide trust VMware production-ready technology to consolidate and standardize their data centers. With their virtualized data center, the state of Michigan was able to achieve their objective of agility in delivering solutions, improving communications across business units, and reducing costs, an important factor for a financially strapped state budget. With virtualization, an investment of $1.6 million yielded $5.25 million in CapEx savings and over $850,000 in labor cost savings, while the time to deploy new applications into production was reduced by approximately 35%. Managing future growth while reducing cost and complexity in a siloed data center is no longer impossible. Data center virtualization and consolidation helps your IT team reduce capital expenditure and eliminate inefficiencies, en route to meeting increasing growth demands and delivering virtualization economics across the data center, and ultimately expanding to the hybrid cloud to open the door to new services and business innovation. Learn more about how the software-defined data center can transform your data center at vmware.com/it-outcomes.
Little disclaimer again, as you know, I'm not paid by VMware, but they have nice videos. We break here for 10 minutes and then return to the second part. Thanks. One second, I just have to stop the recording here. Oh. Oh.